So this is the second part of section 6.1. So if you haven't watched the first part, please do that first. Otherwise this won't make any sense. But if you already have, this is the continuation of it. All right. So we're going to do more word problems. All right. So just kind of a reminder, y equals a1 plus or minus the rate to the t. Okay, this is our general consensus of how we would write this if we want our rate. And our rate is as a decimal. Okay, now remember, if this is a plus, then this is exponential growth. If this is a minus, then it's exponential decay. Typically speaking, a is our starting value. And t is generally, now this can, change a lot, but g is generally our time. A lot of times it's in years. All right, so if I look at example 4a, it says, suppose a new piano costs $8,500 and depreciates 6% each year. Okay, write an exponential model that gives the piano's value when it is t years old. So t's represent years. All right, so y equals, all right, so a is our starting value. Okay, well, our starting value is $8,500. Okay, 1, okay, plus, well, it's depreciating, so that means it's going down in value, which means this would be a minus, and it's 6% each year. Well, we wouldn't write minus 6. We would want to write this as a decimal. So 0.6, or so 0.06 is 6%. So 0.06 to the t power. Okay, so if I want to clean this up a little bit, y equals 8,500, 0.94 to the t. Here is my equation. Right, now on B, it just wants to predict how much it'll be worth when it's 5 years old. So we just plug t equals 5 in. So y equals 8,500, 0.94 to the 5th power. And if you put that in your calculator just like that, you would get roughly 6,238.18 is what I got. All right, if you want to try this on your own, pause it and try it on your own. You surely should be able to do it. But if not, I'll walk you through it. Okay, so remember, we want to use the form y equals a 1 plus or minus our rate to the t power. Okay, so it says, in 2000, the world population was about 6.09 billion. During the next 13 years, the world population increased by about 1.18% each year. So here's our rate, here's our starting point. Write an exponential growth model in populations. Now notice, it's already going to be in billions, so we could just write 6.09. T years after 2000. All right, so y equals, now our starting rate is 6.091. Okay, now are we adding or subtracting? Well, we're increasing, so we're going to be adding by 1.18%. We want that as a decimal, so that's 0.0118. And once again, that is to the t power. Okay, so if we want to simplify this, it's just y equals 6.09, 1.0118 to the t. And remember, t is years since 2000. And y, don't forget, is in billions. Okay, so B, it says estimate the world population in 2005. So that's just when t is 5. Okay, so 6.09 times 1.0118 to the 5. And when I do that, I get 6.46. And remember, that's billions of people. All right, if I look at part C, it says estimate the year when the world population was 7 billion. So we know our population is 7 billion. So I'm going to say 7 equals 6.09, 1.0118 to the t. Okay, now if I subtract 7 from both sides, I get y equals 6.09, 1.0118 to the t minus 7. And then I want to see where this is equal to 0. All right, so when I graph this, this is the equation I got, and notice it crosses right just under 12 at 11.871. So if I go back here, this is roughly when t is about 12. Now remember, t is years since 2000, so that'd be in roughly 2012. That would be the year. All right, let's look at example 5a now. Okay, now this is kind of the same thing, but we're going to have to do one more thing. Okay, so it says the amount Y in grams of a radioactive isotope chromium-51 remaining after T days. Here's our equation. Okay, so we're given our equation. T over 28. Okay, where A is the initial amount. What percent of chromium-51 decays each day? Okay, so if we're talking about each day, we're talking about 1 day. So T is 1. Okay, now some of you are looking at this and say, how do we know that if we don't have initial amount? Well, we don't have to. Okay, because all we want to know is how much it decays in a day. So this is our decay. All right, so we're going to do 0.5 to the T over 28. Okay, and we're going to work this out. So this, if you remember, property of exponent is the same thing as 0.5 to the 1/28th power to the t. Okay, and if I put this here in my calculator, I would get 0.9755. Okay, so this equation right here in red and the equation y equals a 0.9755 to the t, these are the same exact things. Okay, so now I want to get the rate at which it decays. Okay, so I want to write that in the form a 1. Obviously this is less than 1, so it's going to be minus a number to the t. This would be my rate. Okay, so if I want this to still equal 0.9755, oh, I missed a 7 in there. My number here would have to be 0.0245. Okay, or remember, this is my decay rate, so 0.0245 is roughly 2.45% daily decay rate. Alright, if you want to try this one on your own, I encourage you to do that. It's very similar to A. Here's your equation. If not, I will go over it with you. Alright, so we have y equals a 2 to the t over 3. Okay, so we want this just to the x, so we're going to rewrite it. Y equals a 2 to the 1/3 to the t power. Okay, and if I put 2 to the 1/3 into my calculator, I get roughly 1.2599. Okay, now this is obviously more than 1, so I can change that to a 1 plus 0.2599 to the t. And remember, this right here is my rate. Okay, so because this is a plus, I have a growth rate of, and as a percent, this is 25.99%. Growth rate of 25.99%. I'm going to put daily right here. Alright, so one of the big things you hear of exponential growth is when you're talking about compound interest, okay? So you will need to know this equation for the test. So this is the equation for compound interest here, where P represents the principal. The principal would be basically the starting value. Okay. R represents the rate. And don't forget, it's usually given to you as a percentage. You want to put it in decimal form. Okay. T represents the time in number of years. And N is the number of times compounded yearly. So in other words, if it says compounded annually, our N would be 1. If it's compounded semi-annually, that's twice a year, N is 2. If it's compounded quarterly, that'd be every 3 months, so 4 times a year. If it's compounded monthly, N is 12. All right, so let's look at a problem. We're going to use A equals P, 1 plus R over N to the N times T power, okay? You're going to have to know this. Okay, so you deposit 8600, so that's our principal. An account that pays, here's our rate, but we want to put it as a decimal, so it's 0.0132 annual interest. Find the balance T years, so T is 4, when the interest is compounded quarterly. Okay, so if it's compounded quarterly, quarterly is 4 times per year. Okay, so we're just going to plug all these into this formula. Okay, so A equals 8600, 1 plus my R is 0.0132 over N, which is 4, times N, which is 4, times 4 years. Okay, now if I put that all into my calculator, I would get my A is roughly $9,065.49. Guys, because this is in dollars, don't go out like 8 decimal places, okay? Just 2 for cents is fine. All right, I highly encourage you to do these 2 monitoring progress on your own. So go ahead and pause right now, do those 2, and then once you're done, go ahead and check to see if you have the right answer. All right, so this is what you should have got for the first monitoring progress. And this is what you should have gotten for the bottom one.